帮我把这个给
我连个不用连，你是心里里面的呗。
不是你一会儿帮我给验证好吧？
这给验证是吧？
给验证对，给验证。
那这个验证跟验证会来吗？
他说他今天来的。
他今天那个有事，那星期他跟我他放我这了，他来一个找我。
他跟我说他来的。
啊，
谢谢你啊。
不会。
Yes, everyone's early. So, yeah. Well, many of you here, here's a summary of the things I talked about yesterday. So if there's any questions, you can have questions now before we start. I don't want to do that. Just because I got. Yeah, okay, that's good then. So somebody will take a look at tomorrow morning.
今天时间点位，李新平到，谢天阳到，朱生南到，段旭李伟。 张家豪、白凯、刘辉、刘小雄、陆亚磊、洪真、吴红、张文璇、莫家豪、方一梅、高恒、张婉培、冉兆、周居、王子、江秀才、侯锦新、高铁健、段一伟、陈朝辉、何永旭、高原、华阳、黎浩书、算哪个？好，可以这样。刘丽雪，刘正，刘行哲，汪景波，王晴晴，徐慧生，杨全生，玉芳堂，何伟壮，光赞，张家龙，白小晨，黄云红，许飞，梁晨光，冯世宇，石尚，杨超，邱长明，张燕，周国珍，周旭聪，张廷耀，朱晨曦，
刚才叫
对了王方文，吴淑山，
不是这里，
就这么下。
剩下的待会儿，
我还要去。
本来以为你吃的，但是好像被
你点名有全点吗？没有全点，本科生还没点。
接下来那个我们昨天注册的是上面没有我们的名字是吧？
还没名，就没。
昨天那个，好，我们刚才
另外中间还会点。
刚才
哪个点？
签过了是吧？这个是新的吗？
没签过，等一下我。
你说一下，课前。
全是本科生吗？本科生没有，本科生研究生。等一下，本科生研究生那边点吗？有。研究生点完，我没有点到我的。没点你的。
教材还没到。
你叫什么？下午周伯珍。现在还没。周伯珍点过了。你没念错了。
还有那个我的也没找。
点过了，打过了。
我的我。
大家先上课吧，课间有问题再来，好吧？
你本科生还没点？这是研究生的，我点。
研究生的。
点过。
我点过，但是我刚刚看到。可以了吗？
可以，没问题。
就是在开业，就是那个。
你本科生吗？
不是。
然后关于教材的问题是，
点过了吗？作业群也到了。
打印拿过来嘛。
这个没点，这个没点，
就大家都注册完的拿完了有多你再拿，好吧？不然会导致有些注册的人拿不到的，肯定是注册的人交了钱。
Okay, well, good morning, everybody. So let me just summarize some of the things I talked about yesterday. So I talked about the Z2 gauge theory model, which something that wasn't physically motivated by any particular reason except as an interesting model to study. It was a model where you had qubits on the links of a square lattice. Every link of the square lattice, there was a two-stage system. And you couple them together subject to certain local symmetry. So it seemed like a model that had a huge amount of local symmetry. There were these operators G sub I, which commuted with the Hamiltonian. And that was crucial to its structure. Anyway, so we fixed the GI to be 1, and that restricted the Hilbert space. And then we talked about the dynamics of that model on this Hilbert space. And what we argued that there was a phase transition, and this, in some sense, historically, is the first example of a phase transition without an autoparameter, without any local observable non-symmetry rating. And roughly speaking, today we call that phase transition a topological phase transition, a phase with topological order to no topological order. And I define topological order as just the ability to create local excitations, and the existence of local excitations which cannot be created by a local operator. So the fractional quantum Hall effect is like that, and here these fractionalized excitations were these pi fluxes. Any operator would create a pair of them, not just one of them. And just the existence of these excitations led to other properties that we also talked about. I also mapped the theory onto another theory, which is a little more complicated. Let me not say anything about that right now. As long as you understand the basic phenomenon, then we can go ahead with it. Okay? So any questions on this side? And there's a fairly detailed discussion of all the issues in the notes, including a discussion of the nature of the phase transition. The phase transition turns out to be dual to the three-dimensionalizing model, and that's derived in the notes, and but I won't go into that. So, okay, that was all interesting, but you might be left with a feeling that, okay, that's very nice. Here's a model that has a phase transition between an autoparameter, but it's a very strange model with all these local conservation laws, local symmetries, infinite number of local symmetries, and therefore it has nothing to do with the Hubbard model, which doesn't have any infinite number of local symmetries at all. So why should I care? And in some sense, that's why nobody cared. Even though this was discovered in the 1970s, nobody really thought it had anything to do with anything in condensed matter. Because there are all these local symmetries that simply are not present in the real world. Okay. So today I want to show you that despite this problem, even an ordinary model like the Hubbard model can, on its own, be in a phase which has the same topological order. And you can introduce the local symmetries by hand by introducing redundant parameterization of the degrees of freedom. And that, you might say, why should I introduce, a redundant parameterization when I have a non-redundant parameterization? That's a good question. You don't have to. But if you want to talk about topological phases, as a redundant parameterization, make it easy. It gives you a language to talk about new types of phases that the regular parameterization does not allow. So that's roughly the idea. So, but before I get to the Hubbard model in the first hour this morning, I'll talk about a much simpler model, just the XY model. Okay, so now, for at least the first half of the lecture, I'll actually talk about classical stat mech. And this will be classical stat mech in 2 or 3 dimensions. Okay? Now, there's a mapping of classical stat mech, say in 3 dimensions, to quantum models in 2 dimensions. Where 1 dimension of space becomes a dimension of time. So this is a very familiar mapping. My book on quantum phase transition has several chapters deriving it. I won't go to it. I'll just kind of assume the main results. So in particular, everything I would say in the first hour could equally well be applied to a quantum model in 1 lower dimension, So I'll use little d for the quantum dimension, space. Capital D is like the dimension of space-time. And it's basically the Bose-Hubbard model. Sorry, I should have said here, an integer filling. That's very important. So there's a very well-known connection between the Bose-Hubbard model, the integer filling, one boson per site or two bosons per site, and XY models in one higher dimension. I just assume you can read about that, but it doesn't matter if you don't know it. The first lecture is just about then classical XY models. Okay, so this is the simplest classical XY model. There's an angle theta on every side of the lattice, and the action, there's some Hamiltonian. It just depends on this angle theta. This is not really just an energy. It's not even a Hamiltonian. And this Hamiltonian has one global symmetry. It has the global symmetry that which is that theta I goes to theta I plus a constant. If you change all the angles by a constant, then nothing changes. So that, and then also it has a periodicity in theta, which is theta I goes to theta I plus 2 pi n I, these are arbitrary integers. So with that constraint, the simplest coupling you could have is just cosine of theta I minus theta j between nearest neighbors. All right, so this is the classical XY model. And it has, this theta has many interpretations. It could be the orientation of a spin, which lies in a plane. It could be the phase of a Bose condensate at finite temperature. So the lambda transition in liquid helium is described by this model at finite temperature at 2.4 Kelvin. Anyway, so I'll just review some basic properties of this XY model. And one other thing I should mention, which I also kind of assumed yesterday. So this is a model defined on the lattice. And at some point, you want to write down some long wavelength theory for the fluctuation of these phases. And the way that's usually done in classical stat mech is you define a complex field, psi, which is just this phase e to the I theta. And then, of course, as defined, this implies that mod psi I squared equals 1. So, if you keep that into mind, then the modulus of psi has no meaning. But there's this very standard RG procedure where you define your psi, so you have some region here. On every side there's an angle theta pointing in some direction. So you do this coarse graining operation, you take some region R, and in this local region R, you define psi of x in this region, and this is some region x. It's somehow the average of x, of I belonging to the neighborhood of x, of e to the I theta I. So if you do this, we define psi to be some local average, and then psi need not be a unit modulus. So this way you do some coarse graining, you go to long distances, and you write down a continuum field theory, and this is the field theory, this is the 5-fold field theory of a complex scalar. And this term here gives you this, and then you just put in a phenomenological potential, sort of like the Landau-Ginzburg theory. And this partition function then is the starting point for the theory of the critical properties of this theory, okay, of this model. So this is a very standard procedure in stat mech, in theory of phase transition, classical stat mech, which led to the Nobel Prize for Ken Wilson in 1982. So I did a lot of that yesterday too. When I went for the Higgs field, I just assumed you knew this step. So you can also have a gauge field and put the gauge field in here. And so, okay.
So if I flip I and J, this also related to the same thing. Flip I and J.
Flip I and J. I and J are sites. Oh, you mean so some kind of time reversal symmetry? Theta goes to minus theta.
Let's change I and J.
Yeah, so I'm assuming spatial inversion symmetry. Yeah. Yeah, so that's ready to time reversal in most cases. Yeah. So I'm assuming spatial inversion and time reversal symmetry. Okay, so what do we know about this model? Well, we know a lot. So there are two basic, and there's a huge difference in this model between d equals 2 and d equals 3. And let me just remind you. So in d equals 2, as a function of temperature, you have another example, which is a later example, but this is the example that got the Nobel Prize in 2016. You have the crossless-Howless condition. So you have, this is temperature T, and this is the temperature called the crossless-Howless temperature. And in this case, you have no condensate. There's no condensate at finite temperature in two dimensions in either phase, so there's no broken symmetry. And so this is another example of a phase condition without a broken symmetry. And what Crossless and Howless showed was that one way of distinguishing the two phases is by the correlation function, psi of 0, psi of r. Well, this decays with the power law, some eta here. And over here, this psi star of 0, r, psi of 0 decays exponentially as r goes to infinity. So this is called, sometimes called quasi-long range order, and this is called short range order. So as correlations decay exponentially, well, there's no order at all, but here it's almost long range because this is a very slow decay at long range. Okay. So that's what distinguishes the two phases. But more importantly, there's also another difference between these two phases, which is actually similar to this, that here the vortices are expelled, and here the vortices are not expelled. So what are these vortices? The vortices are in your two space dimensions, and the vortices are exactly what you would think. There's like so here's a topologically stable configuration, and then you throw that around in a similar way, like that. So if you go very far away from the core of a vortex here, you take some big contour C, so then around the contour, grad theta dot grad theta dot dx along this contour is 2 pi times an integer. So these are vortex configurations that are allowed, topological defects that are allowed in the xy autoparameter. And what Crossless and Howless showed was that in this phase here, the vortices are not present, and here they proliferate. Okay, so that way it's very similar to here. Here the vortices or the anode of the vortices with a pi flux, which is not present here and proliferates here. Okay, so somewhat very similar, but there's one difference here. You don't really need this explanation to distinguish the phases. You can already see the distinction by looking at the local observable. There is still a pretty clean distinction between these two, just locally, by looking at this correlation decay. But it doesn't go to a constant as r goes to infinity, it goes to a decay. So that's what happens in 2 dimensions. So this is then another example of a topological phase dimension. This question of taste. Does this have topological order or does not have topological order? It depends on who you talk to. Some people say yes, it does. But by this definition of expelling defect, it does have topological order. All right. So everyone familiar with that? Or if not familiar, hopefully you have some idea what I'm talking about. Any questions? Yes.
What distinguishes this from an actual disorder?
Short range is another word for disorder. Okay. Yeah, so there's no, if you go to infinite temperature, there's nothing. It's exactly the same. At infinite temperature, the correlation line becomes, one line less than one line is spacing. Okay. However, something is very different in d equals 3. So let's talk about d equals 3. Then that's the more conventional scenario where mean field theory applies, at least away from the critical point. And then we have as a function of temperature, you actually have true symmetry breaking. So here you have this long range order, this is short range order. And then here psi of r of 0, correlation function r goes to infinity is equal to some, is not equal to 0. Where here r 0 again falls over. And that's it. Now, so this is a true phase which is with symmetry broken, and the broken symmetry, this is a conventional phase condition, and here is no broken symmetry. And the symmetry, of course, is that symmetry, theta goes to theta plus a constant. That symmetry is broken in one case. All the sides pick a common phase, and there's true long range order, and here they go. So this is the analog of what's called the Curie transition of a ferromagnet. The Curie-Weiss mean field theory from the 1920s and 30s basically was developed to describe something like this. And it's basically correct. Except when you get very close to this critical point. And when you get very close to the critical point, and there's all kinds of interesting critical fluctuations, and the whole renormalization group was developed exactly to understand this transition, and it's understood by taking the continuum limit, the RG on this theory, and the epsilon expansion, the one-to-one expansion, and there's so much technology that came out of understanding this phase transition, which is all pretty well understood today. And that's what led to the Wilson's Nobel Prize in 1982. This one, a long time ago. And this was not until very recently, 2016. We can also try to think of this in any case in terms of vortices if you want. And actually we do want, because it'll be important for what I want to talk about today. So here you could say that the vortex, so what, in 3 dimensions, these are not point vortices. This is a line, okay? So the vortices actually come in loops. So it's like a fluid, and if you just shake it up, it will have vortex loops, like a smoke ring, and lots of those types of fluctuations. So they are vortex loops, and roughly, although you can try to form a description using vortex loops, and there's a lot of success in that, but we won't do that today. So here you have the vortex loops are expelled. There's hardly any vortex loops at long distances, and here vortex loops proliferate. There's lots of these. Everything is disordered, and things are fluctuating so strongly at high temperatures that you can't even identify the vortex loops. Okay. There's so many of them. All right, so this is then phase transition 101. This is a 3D XY model, a 3D Heisenberg O3 model, and the Ising model, the 3D Ising model. Very similar behavior, and they're all described except right in the critical point by ordinary mean field theory. Okay, so this should be a topic of some advanced StatMech course. You learn about that. All right, so that's also hopefully a review. And any questions yet? Okay, so what I want to do is ask the question, can you have in this XY model a phase transition in 3 dimensions which is not symmetrical? Okay. And that's what we're looking for. And the XY model is a much more natural way to look for such a thing rather than the Z to gauge theory, because there is no local symmetry. This is the model, and there's only one local symmetry. All right. So that's the question. Okay, the answer turns out to be yes. People have shown this in the 90s and early 2000s, and the references are in my notes. So the way we're going to think about it is because, of course, if I take this model, it's a very definite model I wrote down on the board. I don't know when this model was probably studied starting in the 1950s and 60s, and a huge amount is known about it. Everything I've written here is correct. That's the complete theory. There's nothing else. So we want to deform the model somehow. We want to add other couplings. And we want to add couplings that are not just simple as this. So I'm going to try to add slightly more complicated couplings. And in particular, I want to add not 2 body terms, but 4 body terms. Suppose I add a term like this, minus some I, J, K, L, K, I, J, K, L, cosine theta I plus theta J, minus theta J, minus theta L. Of course, I have translational symmetries, spatial inversion symmetry. I have all the symmetries. I preserve them, but I have some terms like this, coupling the spins, especially around the plaquette. Okay, so I'm going to try to play some funny tricks locally with interactions that are not completely on 2 body, but have some 4 body interaction around the plaquette. And I'm going to vary the magnitude of the K's with lots of possibilities and ask what is the phase diagram. Is there anything else? Are these still the 2 phases when you modify this model by some 4 body terms? Okay, that's the question. It's a very well-posed question, and there could be many possible answers. And in fact, there's a lot of richness here, but I'm going to focus on a very particular model for which we know the answer. And there is, in fact, a whole new phase here that's missing. This phase diagram is not the complete phase diagram of the 3-dimensional XY model. All right. So, but this form of writing it is very complicated, and it doesn't get us very far. This is already a hard enough model, and I've made it even more complicated. So I'm going to propose a particular model of this form. So this is the model I'd like to solve. That's too complicated. So once I include these terms. So I'm going to propose another model. And that's the model I'm going to talk about. So I'm just going to pull it out of my hat. And this model is, as you'll see, cleverly designed to do what I want. But it's just a version of that model. Okay? So let me write down the model that I want to study. So what I want to study, let me call it Z tilde of XY. And we'll have product that I against Z tilde over 2 pi. But it'll also have sum on sigma ij plus minus 1. So there's going to be some auxiliary variables that I'm going to introduce, which looks suspiciously like a gauge field, but I'll try to convince you I haven't done anything that strange or dangerous in a little bit. Just want to make sure about the same notation here. Yeah, so that's right. Sigma ij of plus minus 1 of e to the minus of h to the p tilde, and h tilde will be minus j sigma of h. is the model. Now this model is defined by this angle theta as before, but there's a new variable which is sitting on the bonds. And that variable has two values, plus or minus 1. So these are bonds in the three-dimensional lattice. It's a classical Ising variable, which is sitting on every bond. Okay? So on every bond of the lattice, every bond of the lattice I have, this is a three-dimensional lattice. This is a cube sitting here. And then I have the theta 1 here, theta 2. And then over here I have sigma 1, 2, which is plus or minus 1. And so this is theta 3, sigma 2, 3, and so on. All right. So I just write down this Hamiltonian where I have this cosine term here, but the sigma ij in front of this. And this is the product of sigma ij on the plaquette. So this term would look like, this is sigma 2, 3, so this is sigma 4. So that term would be sigma 1, 2 times sigma 2. So the term like minus k, sigma 2, 3, sigma 3, 4, sigma 4, 1. That's what this term looks like. All right. Now, when you just look at this, you changed everything. You've introduced this new Ising gauge-like object, and this is all cheating. Well, okay, maybe it's cheating, but no, not really. What I want to argue that this model here is basically of this type. It's a particular choice of the KIJKL, and it also has I have many other terms, but they're all of this form. And the way to do this is to just do the sum over sigma ij. So perform the sum over sigma ij in powers of k. And then you will find that this will show that h tilde basically goes to h. Okay, why is that? Well, let's take the 0. Suppose k was 0. Suppose k was 0, and then I sum over sigma ij. When I do this sum before I do the integral. I'm just going to do the sum. And when I do the sum, I claim that this integral over theta will look very much like this integral. Okay. So what happens? Suppose I do the sum, k is 0, I just do the first term. So this is just, if I just look at this term, it's sum on sigma equals plus minus 1 of e to the sigma some cosine theta over 2. And that becomes something like cosh of cosine theta over 2. And now the important point is this is some function of the angle difference. For this function, when theta goes to theta plus 2 pi, it comes back to itself because the cosh is an even function. So notice there's an angle. So it might seem that this thing is not periodic if theta goes to theta plus 2 pi. If I naively perform this operation on this term, then this changes if these two are different. Then if we just take theta I to theta I plus 2 pi, this changes sign. But the point is that when I sum over sigma ij, I can compensate for that change in sign. And I get a term that's totally periodic in theta goes to theta 2 pi. So this is periodic in theta goes to theta plus 2 pi. So I can put this up in the exponential, okay, and then expand that out. Okay, it'll have a term like this, it'll have cosine of twice this, cosine of 3 times that, and so on. So it's very much of this form. And then you can show that for higher order terms too, in each power of k. When you take power k to the 4th, you'll finally get a term where you get the theta going around the plaquette, which will be a term of this type. Okay. So when you go to higher order in k, this k is something like this. So k to the power 4 will give you a term of this type. previous terms, don't give you anything because many of the terms vanish when you do the sum over sigma ij. And so it's all cleverly designed so when you do the sum that this would be reproduced. Okay? So this is just to show you that this looks like some kind of theory with a local symmetry, and in fact there is a local symmetry. I'll talk about it, but the local symmetry is entirely fake. You can just get rid of the local symmetry by doing the sum over sigma, and then you get a model that's exactly of the structure that you're interested in. There is any kind of model with short-range interactions where you preserve these two important properties. All right. So now let me make the local symmetry explicit. So in this particular theory, when I'm doing the integral over theta and setting over sigma, I actually don't have to do the full integral because this Hamiltonian does have a local symmetry. But the net symmetry is entirely a consequence of my introducing fake degrees of freedom. This is not anything real. It's not anything I can measure, the sigma ij. It's just a trick for rewriting this in this way. It's something like what sometimes we call the Hubbard-Fraternalist transformation. It's not something like, it's like a local Hubbard-Fraternalist transformation. It's not introducing any degree of freedom. It's just introducing a redundant parameterization. And that's very, very useful, as you'll see in a minute. So redundancy can be good. And sometimes you want to introduce it even when you don't need to. Oops. All right, so what is the local symmetry? So this particular action has a local symmetry, and the symmetry is the following, is that take theta I, that is theta I, that's pi and 1 minus rho I, and sigma ij, so sigma ij, rho I j, then rho I plus or minus 1, and then under this transformation, h tilde is invariant. So this is very easy to check. Just plug it in there and see what you get. So of course when rho I is 1, then theta doesn't change, and sigma ij doesn't change. When it's minus 1, then what will happen when you do this is that, okay. So if this is minus 1, that cosine term will change by minus 1. But the sigma ij will also change by minus 1, and that will exactly compensate. And this never changes the product of oblique x, because every rho I will appear twice. So there is a local symmetry where rho I can be independently plus 1 or minus 1. So so I've introduced something that I introduced the extra degrees of freedom, but then I've introduced some redundancy in the parameterization. So there's many different configurations of the theta and the sigma that have exactly the same energy. And all of those configurations are actually physically the same. Okay? Notice, of course, that under this transformation, this is always an integer multiple of 2 pi, that the physical order parameter that we measure, psi I, goes to psi I. That doesn't change. So that's the clever thing here. This is a local symmetry, but this local symmetry does not act on anything you can observe. It only acts on your extra degrees of freedom that get reduced by hand. Okay. All right, so hopefully I've convinced you of everything so far. Anybody still questioning the connection between H and H tilde? Of course, this is the key property here. That's why H tilde is the same as H, because if psi goes to psi, well, then this is the most general action with that symmetry. right? So this is also of that form, so the physical order parameter does not change.
So then, you see here, even on the flow symmetry,
Sorry?
because the order I did not change.
Yes. Yeah, so it's not really a symmetry, it's not a physical symmetry, but you can think of it as a local symmetry in the new variables in terms of theta and sigma ij. But sigma ij is not observable for that reason. It's not an observable by itself. So yeah, the word is a symmetry. I'm only using it because other people use it. I don't like it either. It's not really a symmetry. It's just a gauge invariance is a better word for it. Sometimes people call gauge invariance and gauge symmetry. People use those two terms as equivalent. I try not to do that. Gauge symmetry is not a symmetry. It's an invariance. But and then I'm going, you read any book on particle physics, theory of weak interaction, and Higgs field. They go on and on and on about all this SU2 and SU2+1 symmetry. Who am I to say that's wrong? But it's definitely misleading. It's not the right way to think about symmetry. All right. So why did I bother with all of this? Well, the reason I bothered for doing this is that this whole approach, the sigma ij have a very nice property. They allow us very easily to measure where the vortices are. They allow you to measure these things. So let's take a vortex, just a straight vortex, which is going out. Okay. So let me actually take a slightly different way of writing the vortex. We'll take a vortex this way, pointing out. Take this vortex. Let's take this vortex. So just imagine that while you're doing the sum over the theta, or the integral over theta, this configuration comes out. Okay? So now if I look at the action, the Hamiltonian, I have to tell you what the values of theta are to specify the energy. And notice this very annoying factor of 1/2 inside the cosine. That means I have to tell you theta, not just the value of theta, but the value of theta, not just modulo 2 pi, but the actual value. So 0 and 2 pi are not the same thing because of that factor of 2, 1/2 in the cosine. So let's just make some gauge choice. So we're going to give some precise values of theta. So let's just call this pi by 4, and this is 3 pi by 4. And this is 5 pi by 4, and this is 7 pi by 4. So there is a branch cut, and the branch cut, let's say, is going here. So as you go farther and farther out, these become closer and closer. This becomes really far away. This will be 0, and this will be 2 pi. And so I'm just keeping track of where the branch cut is. So then I can put the branch cut anywhere I want, but let's say I put it this way. Okay. So coming out of the vortex is a branch cut. All right. So now if I have this configuration of theta, what's the sigma going to do? Let's assume J is very large, and so sigma wants to minimize that energy. So how is it going to work? So what's going to happen? So if I take the cosine of these two difference and divide by 2, I get some small angle. And that small angle has a large cosine. So here, let's say sigma equals +1. So here, sigma will be +1. Here will be +1. Here will be +1. And this will have some energy, this will have some energy, this will have some energy. But here, to compensate for this 2 pi cut, which becomes a pi cut, cosine of pi is -1, so I have to put sigma equals -1. So along the cut, to minimize the energy, sigma will be -1. So sigma is measuring where the cut is. Okay? Here the sigma equals -1, here also sigma will be -1 to minimize the energy, and it will be +1 everywhere else. So if I just look at the value of m, I'm able to look at the value of sigma, I will see the cut. So of course the cut is in physical, and it's going along this direction, and sigma is -1 along this cut. Okay? That will minimize the energy. And now, you put sigma equals -1 on this cut, and the energy of this bond will equal the energy of that bond, will equal the energy of this bond, will equal the energy of that bond. As it must, because the vortex, you can't see the cut. There's nothing physical about it. All the energies should be the same. And they're only the same if you put sigma equals -1 here. Okay? So why is this useful? But now let me take something I can measure, which is the product of sigma around this planet. So let's look at the flux of sigma. That's gauging there. That doesn't change anything. Let's look at the flux of sigma. So here you'll find flux. Sigma equals -1. So here I have the flux. Here, take product of sigma, it's +1. There is no flux. And so there's nothing happening there. And that's good because you cannot measure the branch cut. You can put the branch cut anywhere you want. So if there was a flux here, then that would mean it's going to cost you some energy. Branch cut cannot cost you energy. It's totally a choice of variable. Okay? So here the flux is 0, or 1. Flux is 1. Everything is 1. In fact, the flux is only over here. And this is a very special point. There's something physical about the point. This is where the vortex is centered. That is where the vortex is. It's right there. So it's okay that costs more energy. Yes, but this particular plaquette is going to cost some energy. And that's what, this kind of term will be sensitive to that when there's a vortex. It's going to tell you about energy. Okay? So this tells me, this is the most important point, that you have flux of sigma ij equals -1. That's the same as whole of, this is why I have explained it, all vortices. So what do I mean by that? Well, what I've shown you is an elementary vortex. The smallest vortex is vorticity 1. And what is the vorticity? Vorticity is that into the n. That into the n is 1. And that gives you a net flux of sigma. Now suppose you had a double vortex. N was 2. I can't even draw it. But suppose you had 2 windings. If they were separated because the poles were separated, there'd be 2 fluxes. But 2 fluxes of sigma can annihilate each other. And therefore, there won't be any flux. So what this flux measured is not just, it measures on the odd vortices, vorticity 1, 3, 5, 7. If there's a double vortex, it doesn't measure. It's not sensitive to that. Okay? All right. So now finally, I am ready to make my claim. Everyone happy with this? So this whole trick has been introduced as a way of suppressing vortices. All vortices. Okay? All right, so now I'm going to claim that model over there has a more complicated phase diagram. So the phase diagram of this model with k equals 0 is right here. So now I'm going to evaluate function J and K. So J will become that axis, this J. So this is now J at some temperature to which. But now I'm going to have another axis, which will be K. And what we have learned is that at small k anyway, we have two phases, which will be exactly like there. Which are those two phases here. So here we have x, y, long range. We have long range order and all those properties. I won't write them out again. And here you have short range order, and you have vortices expelled. Okay, now I don't know the precise geometry of the phases, and I'm just trying to think that. So what happens when you increase k? You get another phase. You get a new phase opening up. And the shape of this is not to be taken seriously. Basically, what is that phase? Well, what does k do? When k becomes very large, it makes this vortex more and more expensive. So basically the vortices start disappearing from the problem. There are no vortices. So you might say, okay, once vortices start disappearing, maybe you can't lose your long range order because you need lots of vortices to scramble up the spins. That's what Thalers taught us in 2 dimensions. If you don't have any vortices, then you can't lose them, but it only becomes quasi-long range in 2D. So maybe something similar happens here. But then you realize very large K is not suppressing all the vortices. It's only suppressing the odd vortices. So a double vortex can still appear. And if J is small, those double vortices will have very little energy, and they can start to fluctuate and disorder everything. So effectively, you'll have a condition where the double vortices take over, and it's as if, since you don't have any fluxes in sigma, you can put all the sigma equals 1. You choose the gauge where sigma equals 1. Now, if you choose the gauge where sigma equals 1, then this becomes an XY model, but an XY model of half angles. The periodicity is theta goes to theta plus 4 pi, which is why the most elementary vortex is a double vortex. Okay, so here you have a phase with short range order, where only odd vortices are expelled. Okay, and that's the main thing that I wanted to show you. There's another phase, even in 3 dimensions, and there are a lot of numerical studies that have verified this. References are in notes, where you have topological order. And my claim is that you can get topological order in just some more complicated model like this, or even in the Bose-Hubbard model with some ring exchange terms. So you need some ring exchange terms like this, that's all you need. And then you can get some kind of non-superfluid phase for the Bose-Hubbard model, or some disordered phase for the XY model, which has this property that there are lots of vortex loops here, but all the vortex loops are double vortex loops. They're like pairs of vortex. They're bounded. So you have vortices, and then you have a kind of a binding, unbinding transition. Here there's lots of vortex loops, all elementary, and here they all bind into pairs. And that's this space. All right, so that's a thing that can happen in the 3D XY model, purely classical XY model we thought we knew understood everything, but it has a very novel type of phase transition where if I go this way to this way, there's no broken symmetry. So this is a topological phase transition. Okay, and now comes another very important statement. What is the nature of this phase transition? Well, my claim with this phase transition is exactly the phase transition we talked about yesterday in the Z2 gauge theory. So the Z2 gauge theory was a very special type of model with all these seemingly local quote-unquote symmetries. And my claim is that this phase transition between the two disordered phases of the XY model can just be viewed as a phase transition which is described by the Z2 gauge theory. And how do I see that? Well, it's very simple. Here, these are both short-range ordered phases. So theta is fluctuating a lot, or another way to say it, J is very small. Now when J is very small, just go ahead and expand that, reverse the orders of summation integration. So what I said earlier, to show that this is an XY model, just sum over sigma ij. And then you get that model over there. But now let's do it the other way. Let's put this on this side and put this out here. And then this one inside. Do the integral over theta and do the integral over theta in powers of j. You can do it. And when you do that, you get this term, which is basically the Z2 gauge theory, plus some corrections, which will all be of this form. All the terms you will get have to be gauge invariant, as in the last slide. So that is just the Z2 gauge theory. So this whole region, this transition, this topological phase transition, as in Z2 gauge theory. So that's the main message. The Z2 gauge theory is not something bizarre or strange that condensed matter physicists should know about. In fact, we should know about it. It's really crucial, and it affects the phase transition and the phase diagram of even something as simple as a 3D XY model. Something that models and studies in the 1950s can have a phase transition without a local order reference. I mean, there's a theta, but the theta is just exponentially decaying in both phases. Nevertheless, there's a change in topological structure. So what this tells you, in fact, that this phase here where the vortices are bound into pairs is the same structure when interpreted as a quantum model in 2 dimensions as the toric code. It has all the properties of the toric code. It has M particles. The M particles of the toric code are precisely the odd vortices. This becomes an M particle, which is got a branch like going around. Now, you know the toric code has an E particle. You take the E particle around the M particle, it picks up a phase of -1. What is the E particle? The E particle here is e to the I theta over 2. You take e to the I theta over 2 around this, that's a particle. There's a half charge particle. And the half charge particle picks up this phase of -1 and it goes around the vortex. So this is a phase which is just like the toric code. So it has all the excitation structure of the toric code. So I bet you didn't expect that. This is simple XY model has a phase that all the properties of the toric code. It has the E particle, the M particle, it has the fermion, the semyon, sorry, the bound state, the semyon statistics, four-fold identity, torus, everything. The full spectrum of the toric code is this odd vortices expelled phase of the XY model. Okay. So it's certainly a phase that anybody would say has topological order. No one would disagree with that. And this was actually discovered long before the toric code. All its properties were understood. Incidentally, this wasn't appreciated. Okay. Further questions? All right. So I'm almost done with this part. Let me just end by rewriting this theory, which is, you can think of this theory as some Z2 gauge theory coupled to a scalar matter field, which is cosine theta over 2. Let me write it in the continuum. So I'll just take this theory and write it in the continuum. So I'll do that. then you will also see more explicitly what I mean by the E particle. So this is what I did at the end of last lecture. It's a little, hopefully now it becomes a little more familiar. So continue. Formulation as a V2 gate, as a U1 gate theory. So what happens there, if you remember that sigma ij goes e to the exponential I aij. And then remember we had Lagrangian for the V2 gauge theory by itself was grad IA plus 2IA Higgs field squared so this is what I had yesterday. And now what's new is that I have this theta over 2, so I'll call that little psi. As you know, I'm going to use psi for that. So just to be this, my notes you call it little psi, but I'll call it phi. E to the I theta over 2, the half angle. And that, hops around with the sigma ij gauge field, which becomes this gauge field, and has charge 1. So that would be IA phi squared plus, let's say, d tilde phi squared plus d tilde phi forward. And then I they also have to worry about monopoles to get everything right, but let's forget about that. And now this axis here, where phi is the autoparameter that condenses and moves this way, and the Higgs field. So what are these phases then? So let's look at the phases. This is the short-range ordered phase. So in this phase, the Higgs field vanishes and phi vanishes. And this is the phase where you have only topological order. And remember, based on I have erased it, here the Higgs field is not 0, but phi is 0. And then the long-range order phase still has the Higgs field not 0 and phi not 0. And so d tilde is sort of an axis this way, and g is basically this way, something like that. All right, so that's another way to interpret this in terms of a continuum field theory. Actually, not quite continuum because of these monopoles that I have not explained. But the point is that it has a Higgs field of charge 2 and a scalar field of charge 1. And this is the E particle. The Abrikosov vortices in this are the M particle. And when you take an E particle around an Abrikosov vortex, they have mutual semiotic statistics. You know what the toric code is. So the toric code, what people call the M particle is phi. Oh, sorry. The M particle is the vortex in H, and the E particle is phi. And this property, of course, is only in this phase. The toric code just sits here. The toric code does not describe this or this. But this more general model has all three phases. All right, so that's all. It's a good time to take a break. But if you have any questions, happy to entertain questions.
So the three-dimension is topological current and this current associated with this vortex or non-Fourier.
Yeah, so there's a dual formulation. in terms of vortex fields. Two vortex fields, one for single vortices, one for double vortices. That's in the notes. That's actually very, very useful because only in the dual formulation can you include the effect of monopoles. You can put a term in the action which allows for the monopoles. So there's a whole dual way of writing all of this. And that's really the ultimate aim for writing things this way. Because it now allows you to make a duality transformation. But you get the same crystals. So if you want to really understand the nature of all three phase conditions, and especially this point, then you need the dual theory. But I haven't discussed that. That's, I've indicated in the notes how that's done.
Another question is the pair of these loops
Yes.
operators. So the two loops can be linked or unlinked.
Yeah, yeah.
How to distinguish that?
That's all included. Those are allowed configuration in all of these formulations. Including linked loops and so on. They're allowed. I don't know if they're that crucial for anything, but they're certainly allowed to